Imagine, if you will, a tiny, seemingly harmless web form.
Right, just a simple blank white box.
Exactly. Just rendering on your screen, asking for a username. It's got that blinking cursor, waiting patiently for your input.
And it looks completely innocent. I mean, you encounter dozens of these every single day.
You really do. But in the wrong hands, that little blank box isn't a login field. It is a completely unbarred window.
Oh, absolutely.
And through that tiny, fragile pane of glass, an attacker can just, climb in, bypass millions of dollars of perimeter defenses, and systematically dismantle an entire corporate network.
Which sounds incredibly dramatic, right?
Right. It sounds like the inciting incident of a Hollywood thriller. But in the reality of modern cybersecurity, that scenario is playing out on servers all across the globe at this very second.
It really is the ultimate architectural irony. Organizations spend incredible amounts of capital building these digital fortresses.
Yeah, the next generation firewalls, intrusion prevention systems, highly segmented networks.
Exactly. They build a wall 50 feet high, and then because they need to actually conduct business with the outside world, they just cut a hole right through the center of that wall.
They literally lower a drawbridge and leave a box sitting there that says, drop your data here.
And if you aren't rigorously inspecting what gets dropped in that box, those 50-foot walls are completely irrelevant. You've invited the threat directly into the courtyard.
Which is exactly why we are exploring this specific battleground today. So welcome to this session of our ongoing deep dive.
Especially to the early career IT professionals joining us.
And, of course, to the students currently working your way through Dr. H.Schuessler's Ethical Hacking and Cybersecurity Operations course.
We're glad you're here.
Now, before we really get into the weeds, take a quick second to like, subscribe, and share this deep dive so you never miss the insider tips that could, one day literally save your career. And definitely check the description for some really valuable additional resources.
Yes, the resources down there are gold.
So today we are crossing a major threshold. This exploration is entirely calibrated to bridge that gap between academic theory and the really harsh, unforgiving demands of the real-world tech sector.
And this is actually the 10th of 14 deep dives we're doing based on the textbook Hands-on Ethical Hacking and Network Defense, 4th edition, by Wilson, Simpson, and Antel.
It's a profound shift in perspective from our last session. Let's just ground ourselves in that shift for a second.
Yeah, let's recap.
In Chapter 9, we navigated the landscape of embedded operating systems, the hidden trust. We mapped out the invisible underlying system.
Right, the routers, the IoT devices, the industrial control systems that are basically holding up the power grid.
Exactly. The core theme there was how implicit trust is often just blindly granted to those internal structural components, and how attackers exploit that deeply hidden foundational layer.
We were essentially looking at the basement of the building. The pipes, the wiring, the systems that administrators set up once and then completely forget about.
Out of sight, out of mind.
Exactly. But today, we are walking upstairs, walking out the front door, and turning around to face the building right from the street.
I love that visual. Chapter 10 is all about hacking web servers. We are leaving the hidden depths and stepping right up to the public-facing storefronts of the Internet.
Which introduces a highly specialized discipline known as application security, or AppSec.
And historically, AppSec has kind of been the overlooked middle child of the IT world, hasn't it?
Oh, completely. Network engineers focus on routing and switching. System administrators focus on server uptime and patching the OS. Developers are just rushing to push new features to meet business deadlines. Right,
so the security of the application itself, the actual logic and code running on that web server, it just falls into this gray area where nobody really takes full ownership.
And because a web server is designed, by its fundamental nature, to be accessible to the public, you can't just enforce a default deny policy.
Yeah, you can't just block all traffic to port 80 or 443. If you do that, your organization essentially ceases to exist online.
Exactly. You have to accept the traffic. You have to engage with the unknown user.
So to understand how an attacker exploits that forced engagement, we need to trace the journey of the data. We have to understand the architecture of the web itself.
Which the source material sets up beautifully by drawing a stark line between two eras of the Internet.
Right, the era of static web pages and the modern era of dynamic web pages. If I'm tracking the evolution correctly, a static page is essentially just a file transfer. The server is acting like a digital librarian.
That is a perfect way to conceptualize it. In the early 90s, the web was almost entirely static. These pages are built using raw HTML, hypertext markup language.
So when your browser requests a static page, the web server just looks at its hard drive, finds that specific HTML file, and sends a copy of it down the wire to you.
Right. The defining characteristic there is immutability. It displays the exact same information to every single user.
So it doesn't matter if it's midnight in Tokyo or noon in London, or whether you are an anonymous guest or the CEO of the company.
You get the exact same file.
It's basically a museum exhibit behind glass. You can look at it, you can read the placard, but you cannot alter the artifact itself.
And from a security posture, that librarian model seems incredibly safe, doesn't it?
Yeah. It is relatively bulletproof from an application logic standpoint, mainly because there is no application logic.
Exactly. There's no execution state. The server isn't processing anything. It's just reading from a disk and transmitting.
So an attacker can't easily manipulate a static HTML file sitting on a server unless they've already breached the underlying operating system or the network, right?
Right, to deface the site or something. But the web service itself isn't a viable vector for complex logical attacks.
But, business couldn't survive on museum exhibits alone. People didn't just want to read a brochure.
No, they wanted to buy the product, check their real-time bank balance, and leave a review.
That demand for interactivity forced a complete architectural redesign. The static librarian had to become a dynamic processing engine.
And that transition to dynamic web pages is the genesis of almost all modern web vulnerabilities.
Because a dynamic page isn't just a file sitting on a disk waiting to be read.
No, it is a page that is constructed on the fly, in real time, at the exact millisecond the user requests it.
So the information varies. It changes based on the user's login session, or their past purchasing history, what's in their shopping cart, or data pulled from some massive back-end database.
So the server is no longer just handing me a pre-printed menu, it's a live kitchen.
I like that. I am walking up to the chef, handing them a custom list of raw ingredients, my user input, and asking them to cook me something entirely off menu.
And that interaction requires the chef to take your ingredients, put them in a pan, apply heat, and actually process them. This is where the risk materializes.
Right, because if the web server's application logic does not rigorously inspect the ingredients you hand over, disaster strikes.
You might hand them a handful of salt, which ruins the dish, or in a cybersecurity context, you might hand them a stick of dynamite and they just blindly throw it into the oven.
Boom. A dynamic page is a two-way conversation. And to facilitate that conversation, developers rely on HTML form elements.
Taking us right back to that blank white box we started with. The textbook provides a really clean structural example of this. It's the HTML form tag.
Right. Inside that tag, you might have an input type set to text for a username and an input type set to password.
Which, by the way, that password input type is just a brilliant piece of psychological security theater.
Because it turns the characters you type into those little black dots or asterisks on your screen.
Exactly. It makes the user feel secure, like they are whispering a secret. But beneath the graphical interface, that form is taking the exact plain text string you typed, packaging it into an HTTP request, and hurling it across the internet.
Just sending it right to the web application to be parsed and processed.
And the text points out a universal truth of software engineering here. Writing a program without bugs is virtually impossible.
Oh, for sure. The complexity of the code scales exponentially with the features of the application.
So by exposing those complex, inherently flawed programs to the entire internet via web forms, you are effectively crowdsourcing the discovery of your own vulnerabilities.
That's a terrifying way to put it. Now, to process that untrusted input, the server needs a mechanism to hand the data off to a program.
Right. And the source introduces a foundational piece of internet history here, CGI, the Common Gateway Interface.
If I understand the architecture, CGI was the bridge that allowed the web server to stop being just a librarian and start acting as a dispatcher.
That is the exact functional shift. Before CGI, if a web server received a request, it only knew how to fetch a file.
Right.
But CGI provided a standardized set of rules that said, when you receive the specific type of request, don't look for an HTML file.
Instead, launch this separate executable program.
Exactly. Pass the user's input to it as environment variables, wait for the program to finish running, and then take whatever the program spits out and send that back to the user's browser.
It turned the web server into a command line interface for the remote user. And the programs that CGI was launching weren't written in HTML.
No, the text lists heavy-duty system-level programming and scripting languages. Things like C, C++, TIV, UNIX shell scripts, Visual Basic, Java, and quite famously, Perl.
Perl. the duct tape of the early internet.
It really was. It was exceptional at parsing text, which is essentially all HTTP traffic is.
The text provides a classic illustrative Perl CGI script. It starts with the shebang line, right? The #/assert/bin/bail.
Yes, which is an instruction to the operating system telling it exactly where the Perl interpreter lives so it can execute the code.
In following that is a print statement, print content type text CML_NNEF.
Right.
Now, those two /n's, the new line characters, that seems like a really minor formatting detail, but in the context of the HTTP protocol, that double return is doing a lot of heavy lifting, isn't it?
Oh, it is the absolute demarcation line of the internet. That content type line isn't meant for the human reading the screen. It's an HTTP header meant for the receiving web browser.
So it tells the browser, hey, the data packet you are about to receive should be rendered as an HTML document, not downloaded as a raw text file or a PDF.
Exactly. And in the HTTP specification, a blank line, which is created by those two sequential new line returns, is the universal mandatory signal that the metadata headers have concluded, and the actual payload is beginning.
The body of the message. And the payload in this simple script is the next line. Print, hello security testers.
So the Perl interpreter runs on the server CPU, generates that string, hands it back across the common gateway interface to the web server daemon, and the daemon ships it across the network to the user.
Meaning the end user sitting at their laptop never sees a single line of Perl. They just see a white page with a greeting.
The server-side execution is a total black box to the client. This is a critical concept for a security tester to internalize.
Because you are interacting with the ghost of the application. You send an input and you analyze the output, trying to deduce the hidden logic running in that black box.
Exactly. But, building massive enterprise-grade applications from scratch using raw Perl or CGI scripts is an agonizingly slow process.
And technology abhors inefficiency. So developers naturally shifted toward utilizing frameworks and third-party libraries.
Which definitely solves the speed-to-market problem, but it introduced a massive supply chain security problem.
Because frameworks are basically pre-built, standardized architectural templates, right?
Right. The text lists several that became industry standards. Spring for Java, AngularJS, Yeoman, SAST, and Vaadin.
And libraries are modular chunks of pre-written code that perform specific, complex tasks, like handling cryptography, or parsing XML, or processing image uploads.
Because a developer doesn't want to spend 3 weeks writing a custom image scaling algorithm, they just import a library and call a function.
I can completely see the business appeal there. Development speed goes through the roof, and you don't need to write extensive documentation for code you didn't write.
But from a threat modeling perspective, this feels like building a skyscraper using prefabricated steel beams that you bought from a total stranger without ever inspecting the metallurgy.
Wow, yeah. What happens when a vulnerability is discovered not in your custom code, but deep inside one of those heavily relied upon frameworks?
It creates a global blast radius. If you write a custom bespoke application and make a logic error, only your application is vulnerable.
An attacker has to specifically target you, map your unique application, and find your unique flaw.
Right. But if a vulnerability, say a zero-day exploit, is discovered in a specific older version of the Spring framework, the attacker has a master key.
Because thousands of enterprises around the world use that exact same framework in the exact same way.
It's an economy of scale for the attacker. As the text explicitly states, as the reliance on third-party libraries grows, the discipline of keeping them current and patched becomes exponentially more critical.
So if an organization lacks a software bill of materials, if they don't even know they are running a vulnerable version of AngularJS buried deep in some legacy web portal, the attacker is going to find it.
Absolutely. Attackers build automated scanners specifically to identify the digital signatures of those outdated frameworks.
Okay, so we have the logic, the scripts and frameworks, but what about the engines actually hosting and serving these pages?
Right, the servers themselves.
The text highlights a fascinating, decades-long rivalry in the web server market. On the proprietary side, we have Microsoft with ICE, Internet Information Services.
And on the open source side, we have Apache.
Let's examine the Microsoft ecosystem first. They needed a way to compete with CGI, which led to the creation of Active Server Pages, or ASP.
Classic ASP was Microsoft's 1998 answer to the demand for dynamic content. It was a server-side interpreted scripting language.
So instead of writing a separate executable program, developers could just embed VBScript or JScript directly into the HTML code.
Exactly. When the ICE server received a request for an ASP file, it would interpret the script, generate the dynamic content, merge it with the static HTML, and send the result.
But interpreted scripts can be slow, right? Because the server has to translate the code line by line every single time a user requests the page.
Right. Which is why the source notes that classic ASP was eventually superseded by a much heavier hitter, ASP.NET.
ASP.NET represents a massive architectural evolution. It moved away from interpreted scripts to a compiled server-side execution model,
heavily utilizing robust languages like C# built on top of the expansive .NET framework.
So when an ASP.NET page is requested for the first time, the server actually compiles the code into a DLL, a dynamic link library, making subsequent requests dramatically faster and more resource efficient.
The textbook provides a really cool snippet of ASP code to illustrate how this blending of HTML and server-side logic looks.
Yeah, there's a standard HTML structure with a head and a title like my first ASP.NET web page. Yeah. But nestled inside the body tags is this peculiar string, %, date time, now %.
Those specific tags, the angle bracket and the %sign, are the trigger mechanism.
When the IAST web server is parsing the document, those tags signal a context switch.
They tell the server, stop reading this as static HTML. The string inside these tags is executable server-side code.
So the server executes the date time. Now function, which queries the server's internal clock, retrieves the exact current date and time and injects that data as a plain text string back into the HTML stream.
Meaning the user sitting in a coffee shop looking at the page never sees the code. Their browser just receives a document that says, October 24th, 2:30 p.m.
The illusion of a static page is completely maintained for the client, while immense processing power is utilized on the server.
But to harness that power, you are generally locked into running Microsoft ISIS on a Windows Server operating system.
Which leads us to a stark market reality. The text provides a sobering statistic here. In 2021, Microsoft ISIS commanded only about 6.7% of the global web server market share.
While the Apache web server held a massive 31.7%. It's a dominant footprint.
So if the .NET framework is as robust as enterprise developers claim, why is Apache crushing ICE in adoption?
Well, the source outlines two primary drivers for that. The first is platform agility.
ICE is deeply intrinsically tethered to the Windows ecosystem.
But Apache is completely agnostic. It was built to run on almost any Nix platform, UniX, Linux, FreeBSD, as well as Windows.
And the second, and arguably more impactful driver, is the economic and philosophical model, right?
Exactly. Apache is open source software maintained by the Apache Software Foundation. It is entirely free.
So when a startup is building their infrastructure or a university is deploying a server, the cost of licensing Windows Server versus spinning up a free Linux distribution running Apache, that's a massive consideration.
Oh, a huge one. The text even notes that the Apache web server daemon, known as HTTPD, is baked directly into Kali Linux by default.
Which means the very operating system used by ethical hackers and penetration testers relies on the exact same server software that hosts a third of the internet.
It creates this deeply symbiotic relationship. The security community understands Apache intimately because they use it daily, which means vulnerabilities are often found and patched rapidly.
All right, so we've established the servers and the basic mechanics of dynamic content, but let's drill down into the specific dialects of the web.
This is where the code meets the vulnerability.
We've touched on ASP, but the source material highlights three other major scripting languages that security testers really must understand: PHP, Cold Fusion, and JavaScript. Let's start with PHP.
PHP, which recursively stands for PHP Hypertext Preprocessor, is essentially the open source counterweight to Microsoft's ASP.
It is a server-side scripting language that gained astronomical popularity because it paired so seamlessly with Apache and MySQL databases.
The classic LNP stack, right? Linux, Apache, MySQL, PHP.
The syntax operates on the same embedding principle as ASP, but it uses the angle bracket $PHP tags.
So if a developer needs to pull a user's profile from a database, they write the PHP query inside those tags.
And again, the security boundary is drawn at the server edge. The PHP code executes entirely behind the firewall.
Right. So if a developer hard codes a database password into the PHP script, which, by the way, is a terrible practice but incredibly common, the user accessing the website cannot view the page source in their browser and see that password.
Because the PHP interpreter strips the code out, replaces it with the HTML output of the database query, and transmits the benign HTML.
Unless, of course, the web server misconfigures the PHP handler.
Oh, right. If the Apache server forgets how to process a .php file.
It might just serve the raw, uninterpreted file as plain text to the user's browser, exposing every hard-coded secret, API key, and line of business logic within it.
That is a classic security misconfiguration, and it really highlights how dependent the language is on the proper functioning of the server daemon.
Definitely. Now, next on the list is Cold Fusion.
This one feels like a relic from an older era of the internet, honestly, but the text includes it for good reason. It's still deeply embedded in certain enterprise and government environments.
Originally created by Alaire and now maintained by Adobe, it operates very differently from the open source PHP model.
Cold Fusion is entirely proprietary. Instead of embedding a traditional scripting language, it uses a tag-based syntax called CFML, or Cold Fusion Markup Language.
The text provides an example tag, CF location URL, www.yz.com.org, add token, no.
It looks very similar to standard HTML tags, but these tags trigger complex server-side actions.
It was designed to provide rapid, tightly integrated development, seamlessly linking the web server, the browser, and back-end database technologies without requiring the developer to write complex connection logic.
But because it's a proprietary monolithic platform, its vulnerability footprint is really distinct.
When an exploit drops for Adobe Cold Fusion, it tends to be severe, often remote code execution because the platform sits so deeply within the application stack.
Right, which brings us to the most ubiquitous and arguably the most dangerous language on the modern web, JavaScript.
This requires a massive mental pivot for anyone studying this. Everything we've discussed so far, CGI, ASP, PHP, Cold Fusion, is in server-side.
The execution happens on a machine owned and controlled by the organization.
JavaScript flips that dynamic entirely. JavaScript is client-side.
The profound implication of client-side execution really cannot be overstated.
When a web server sends a page containing JavaScript, it is taking a package of executable code, handing it across the internet, and saying to the user's browser, "You run this. I trust your machine to execute this logic."
The internet fundamentally relies on trusting the user's computer to execute code honestly. That is a terrifying amount of trust to place in an unknown endpoint.
It really is. The text emphasizes that JavaScript is not a simple formatting trick like CSS. It is a Turing-complete programming language.
It introduces branching, looping, mathematical operations, and the ability to define functions.
It can manipulate the document object model, or DOM, which means it can literally rewrite the web page while the user is actively looking at it.
The book provides a visceral, albeit lighthearted, example to demonstrate this power. It details an HTML page containing a button ominously labeled "Don't click."
And in the header of the document, there is a JavaScript function called chastiseUser.
So when the user invariably clicks the button, the browser's JavaScript engine executes that function locally.
It pops up an alert box stating, "So, you like breaking rules." And then it executes a command to forcefully yank the user's cursor back onto the "Don't click" button.
It's a prank, a digital annoyance.
It is a prank, but look at the underlying mechanics there. A remote server sent instructions to your machine, and your machine obediently altered its own user interface, generated a system dialog box, and hijacked the focus of your physical mouse cursor.
Now replace the prank with malice.
Exactly. If a developer can write JavaScript that pops up an alert box, an attacker can write JavaScript that silently reads every keystroke you type into a banking form.
They can write a script that invisibly scrapes your session cookie and emails it to a server in Eastern Europe, allowing the attacker to clone your login session and bypass authentication entirely.
This is the exact mechanism behind cross-site scripting, or XSS. The text specifically notes that all web-based worms that leverage XSS vulnerabilities are built on scripting languages like JavaScript.
Because the code executes in the context of the user's browser, it inherently trusts the website it came from.
Which is why the source material adamantly stresses that system administrators must relentlessly audit their networks for unpatched or outdated web browsers.
Modern browsers implement really complex security sandboxes to try and contain malicious JavaScript, preventing it from escaping the browser and accessing the underlying OS.
But if an employee is running a legacy browser version that lacks those protections, a single malicious JavaScript execution can compromise the entire endpoint.
Okay, so we have mapped the front door, the forms, and the web server. We've walked down the hallway, the dynamic server-side scripts and client-side JavaScript, but where do all these hallways lead?
What is the ultimate destination for the data collected by these applications?
They lead to the vault, the database.
A web form is ultimately useless if it doesn't have a structured repository to store and retrieve data.
User credentials, credit card ledgers, proprietary intellectual property, healthcare records, all of it lives in a database management system, or DBMS, completely separate from the web server.
And getting the web application logic to communicate effectively with the database server requires a complex layer of technological plumbing.
You have software written in PHP or C# trying to talk to a database written in Oracle or SQL. It's a total translation nightmare.
The source breaks down the evolution of this plumbing through three critical acronyms: ODBC, OLE, DB, and ADO. Let's unravel the first one. What problem did ODBC solve?
ODBC stands for Open Database Connectivity. It was developed in the early 90s by the SQL Access Group to solve exactly that translation nightmare.
Before ODBC, if a developer wrote a web app and wanted it to store data in an IBM DB2 database, they had to write highly specific proprietary code to speak IBM's language.
And if the company later migrated to an Oracle database, the developer had to tear down the application and rewrite all the database logic from scratch.
ODBC was revolutionary because it created a universal translator. It introduced real interoperability.
It provided a standardized library of function calls and data types.
Exactly. The application just sends standard ODBC commands, and the ODBC driver translates those commands into the specific dialect required by whatever database is sitting on the back end.
So the developer no longer needed to know the intimate details of the DBMS.
But technology is rarely static, and Microsoft, seeking tighter integration and higher performance within their own ecosystem, developed a successor, OLEDB, or Object Linking and Embedding Database.
OEDB was engineered to be faster and more stable, moving beyond just relational databases to allow access to data stored in spreadsheets or even flat text files.
The defining architectural feature of OLEDB is its reliance on connection strings and specific providers.
The text lists several of these providers, and they look like highly specialized lockpicks. There are configuration codes embedded directly into the connection string.
For instance, if the web app needs to unlock a Microsoft SQL server, the string must include provider SQLEDB.
If it's targeting an Oracle vault from a Microsoft environment, it uses provider's DORA.
The connection string is the exact set of coordinates and translation rules the application uses to lay the pipe to the vault.
It defines the driver, the server IP address, the database name, and often the authentication credentials required to open the door.
Which brings us to the final operational layer, ADU, or ActiveX data objects. The source defines this as the high-level programming interface.
If ODBC and OLEDB are the physical pipes and the routing protocols, ADO is the mechanism that actually pumps the data back and forth.
ADO provides a highly structured, rigid methodology for interacting with the database. The text meticulously lays out the 5-step process for accessing a database from an ASP web page using ADO.
And this isn't just trivia. Understanding this flow is essential for understanding how to break it.
Let's visualize that 5-step flow. Step 1, create the ADO connection to the database.
So the application initializes the object in its memory, parsing that connection string we just talked about, preparing to build the pipe.
Step 2, open the database connection.
The pipe is built, and now the valve is turned. The application reaches out across the network, authenticates with the DBMS, and establishes a live, active communication channel.
Step 3, create an ADO record set. Now, a record set is a vital concept here.
It really is. A web application cannot and should not pull an entire massive database into its own RAM. It would crash instantly.
A record set is essentially an empty container, a specific object created in memory designed to hold only the exact subset of data you are about to ask for.
It's like walking into a massive warehouse and handing a small, empty cardboard box to the forklift driver.
Which leads to step 4. Open the record set and select the data you need.
The application executes the query. Say, give me the usernames and balances of all accounts in this specific zip code. And the database fills that small cardboard box, the record set, with only those specific rows of data.
The application then reads the data from the box and generates the dynamic HTML page to send to the user.
There's finally the step that developers famously forget. Step 5. Close the record set and close the database connection.
Closing the connection is absolutely critical for resource management. The DBMS can only maintain a finite number of open connections.
If a poorly written application opens a connection every time a user loads a page, but never explicitly closes it in step 5, the database experiences a memory leak.
Eventually, it runs out of available connection slots, new users are blocked, and the application suffers a denial of service failure.
So tying this back to our listener, why does an ethical hacker, a penetration tester, or a student in a cybersecurity operations course need to understand the minutia of ADO record sets and OLEDB providers.
Why study the plumbing?
Yeah, exactly.
Because the plumbing is where the most devastating attacks occur. If an attacker can manipulate the data flowing through that ADO connection, if they can intercept the request or poison the query before it hits the database, they bypass the web server's application logic entirely.
They bypass the login screens, the graphical interfaces, the business rules. They're speaking directly to the vault.
If you don't understand how the connection is structured, you cannot understand how to subvert it.
And that subversion is the essence of application security, or AppSec. We established earlier that it is an overlooked battlefield.
The text really reinforces this, stating bluntly that many security professionals hyperfixate on network security details, tuning firewalls, configuring VPNs, managing Active Directory policies, and completely neglect the application layer.
It's a psychological blind spot. It's just easier to buy a blinking box from a vendor and plug it into a rack than it is to audit 10,000 lines of custom PHP code.
But the consequences of ignoring AppSec are catastrophic. When an attacker gains control over a web server, the damage scales rapidly.
The text enumerates the primary impacts. First, website defacement. This is the digital equivalent of spray painting the front of the corporate headquarters.
It destroys public trust and brand reputation instantaneously.
Second, the destruction or theft of database contents. Customer records, credit cards, healthcare data stolen and auctioned off on the dark web,
leading to massive regulatory fines and class action lawsuits.
Third, the hijacking of user accounts, facilitating widespread identity theft and fraud against the organization's user base.
And fourth, a scenario that terrifies network architects, the use of the compromised web server to pivot and perform secondary attacks.
Because the web server sits in a DMZ, a demilitarized zone. It has 1 foot facing the public internet and 1 foot facing the internal corporate network so it can talk to the database.
If an attacker roots the web server, they now have an internal staging ground. They can launch attacks against highly sensitive internal systems that are completely invisible from the outside internet.
The web server goes from being a public storefront to a hostile beachhead behind enemy lines.
So facing this landscape of vulnerabilities, where does the defender turn for guidance? Who maps the threats?
The source introduces the global authority on this matter, OWASP, the Open Web Application Security Project.
OWASP is a remarkable entity. It's a not-for-profit foundation, totally community-driven, dedicated entirely to fighting the root causes of web application vulnerabilities.
They don't sell a product, they provide knowledge. Their most famous contribution, cited heavily in the text, is the 10 most critical web application security risks document, universally known as the OWASP Top 10.
And the text points out that this list isn't just academic reading, it is so authoritative that it forms the foundation of major compliance frameworks, including PCI DSS.
If your application touches a credit card, you are legally and contractually obligated to prove you have mitigated the OWASP Top 10.
And what's fascinating and slightly depressing is how consistent that top 10 list remains year after year.
The text lists the heavy hitters: injection vulnerabilities, broken authentication, meaning flawed login or session management systems, sensitive data exposure,
XML external entities, or XXE, which is a flaw in how older applications parse XML documents, broken access control, security misconfigurations.
It also highlights cross-site scripting, XSS, which we discussed with the JavaScript prank, insecure deserialization, using components with known vulnerabilities, which circles right back to our discussion about the dangers of outdated third-party frameworks.
And finally, insufficient logging and monitoring. That final point on logging is a silent killer.
Oh yeah. The average time it takes an organization to realize they have been breached is often measured in months, not days.
If you aren't rigorously logging what's happening on your web server, if you don't have a record of every anomalous query or failed login spike, an attacker could be quietly exfiltrating your entire database table by table, and you would be entirely oblivious.
Now, reading about these theoretical vulnerabilities is necessary, but mastery requires practice.
Right, but testing a SQL injection attack against a live, unauthorized production system is a federal crime.
So how do students in Dr. H.Schuessler's course actually build muscle memory safely?
This is another area where OWASP provides an invaluable resource, WebGoat.
WebGoat is a deliberately insecure, intentionally broken online web application designed specifically for training.
It provides a legal, safe sandbox for security testers to practice exploiting the very vulnerabilities listed in the top 10.
The source material provides several visual figures showcasing WebGoat's interface, and it operates like a masterclass in applied hacking.
Figure 1010 details a module called HTTP Basics. It forces the student to look past the graphical rendering of the browser and interact with the raw data transfer.
It challenges them to intercept a GT request, manipulate the URL parameters, and examine the user agent headers.
It breaks the illusion of the web browser. It forces the learner to realize that the browser is just a tool sending text across a wire, and that text can be altered.
Figure 1011 steps up the complexity with a module on SQL injection, intro. It systematically walks the user through manipulating data manipulation language and data definition language.
It differentiates between string injection and numeric injection, teaching the user how to bend structured query language to perform tasks the original developer explicitly tried to prevent.
Which fundamentally is the definition of hacking, making a system do something it was not designed to do.
My personal favorite is Figure 1012, which showcases an admin lost password module. It departs from the tutorial format and operates like a CTF, a capture the flag challenge.
It presents a scenario, removes the hints, and challenges the user to hack the application to retrieve a specific, complex string of characters, which acts as the flag, proving they successfully compromised the logic.
CTFs are incredibly effective pedagogical tools. They rewire the student's brain to think offensively.
They stop looking at an application to see how it works and start looking at it to see how it breaks.
And practicing in a safe, controlled environment like WebGoat is absolutely mandatory because the actual methodology of testing these defenses in the real world is incredibly rigorous and structured.
Let's delve into that structure. How do security professionals execute a formal assessment on a live application?
The source outlines 3 overarching techniques that define the testing landscape. First is SAST, Static Application Security Testing.
To understand SAST, imagine you were a building inspector, but instead of walking through a finished house, you are sitting at a desk reviewing the architectural blueprints.
Exactly. SAST involves analyzing the application's raw, uncompiled source code. You are looking for insecure logic patterns, instances where developers used obsolete cryptography functions, or the cardinal sin of hard-coding API keys directly into the text files.
The application isn't running, it's completely static. But SAST has a massive limitation, which the text highlights.
It requires white box access. It requires the source code.
If a security consultant is hired to perform a black box penetration test against a target, and the client refuses to hand over the proprietary code repository, SAST is completely off the table.
Which forces the tester to rely on the second technique, DAST, or Dynamic Application Security Testing.
Dynamic testing. So the blueprints are locked away, and now the inspector is interacting with the fully constructed building.
Precisely. DAST is walking around the perimeter, jiggling every doorknob, trying to pry open the windows, and intentionally entering the wrong passcode into the alarm keypad to see if it locks out or fails open.
You are engaging with a live, running application. You send it malformed, unexpected inputs, and monitor the HTTP responses.
The text points out that DAST is the ultimate proof of concept. SAST might find a theoretical flaw in the code, but DAST proves whether an attacker on the outside can actually reach and exploit that flaw in a real-world scenario.
And then the source introduces a third, more advanced evolutionary step, IAST, or Interactive Application Security Testing.
IAST is a fascinating hybrid. It takes the deep internal visibility of SAST and combines it with the real-world execution of DAST.
It accomplishes this by placing an agent, a piece of monitoring instrumentation, directly inside the runtime environment of the application.
As the application is dynamically tested, the agent sits inside the memory, watching the data flow through the variables, monitoring the execution paths in real time.
It can pinpoint the exact line of code where a vulnerability triggers during a live attack.
It's like the building inspector isn't just jiggling the doorknob from the outside, but has installed transparent piping throughout the walls to watch exactly how the internal tumblers react when the lock is picked.
That's a brilliant analogy. It provides unparalleled accuracy and reduces the false positives that plague both SAST and DAST.
So a tester selects their methodology, but they don't just immediately start throwing exploits.
The text emphasizes that the most critical phase is information gathering and architecture mapping. Before you launch the attack, you have to meticulously map the territory.
Reconnaissance dictates success. An attacker or a tester will spend days, sometimes weeks, just asking questions of the application.
Does it utilize a database? Does it require authentication? And if so, how is the session token generated?
Are we dealing with static HTML or dynamic PHP? Is there a web application firewall, a wave sitting in front of the server intercepting traffic? How does the data logically flow from the browser to the back end?
The text specifically mentions footprinting to discover the underlying operating system and the DBMS version.
Because an attack payload designed to exploit a vulnerability in a Linux server running an outdated MySQL instance will completely fail and likely trigger alarms if it's fired blindly at a Windows server running Microsoft SQL.
The exploits are highly specific to the architecture. Once the map is drawn, the tester aggressively targets the most common failure points. Authentication and session testing is usually first.
They want to know, when the user logs in, is the data transmitted in clear text over HTTP or is it encrypted via HTTPS?
When the server grants a session cookie, is that cookie randomly generated or is it just the user's ID number encoded in base 64?
If it's predictable, the tester can hijack anyone's session.
And closely related but conceptually distinct is authorization testing. The source makes a critical distinction here that trips up many developers.
Authentication is proving who you are. Authorization is proving what you are allowed to do.
Just because you possess a valid hotel room key authentication doesn't mean your key should open the manager's office or the vault authorization.
The text highlights a pervasive architectural flaw. Developers often rely on security by obscurity to enforce access control.
Instead of checking the user's privilege level on the server for every single request, they simply hide the administrative functions.
They might put the admin controls in a hidden HTML table field or place them on an unlinked obscure URL.
The developer's logic is, if I don't put a hyperlink to the admin dashboard on the regular user's profile page, the regular user can never navigate there.
It's a fatal assumption. An attacker doesn't click links, they manipulate requests.
If they can guess or brute force the URL, say, by requesting adminpanel.php directly, and the server doesn't perform a strict authorization check before rendering that specific page, the attacker bypasses the entire role-based security model.
Which brings us to the zenith of application testing. Input validation. The text defines input validation as the mandatory act of filtering, rejecting, or sanitizing a user's untrusted input before the application's logic ever processes it.
If you fail to sanitize input, the user controls the application. It leads to data disclosure, unauthorized alteration, or total destruction.
And the absolute king of input validation failures, the vulnerability that has dominated the OWASP top 10 for 2 decades, is SQL injection or SQL.
The text provides a highly detailed character-by-character breakdown of a classic SQL injection attack. I want us to really dissect this because understanding the mechanism of this specific string is foundational to understanding AppSec.
The scenario is a standard web application with a login form containing a username field and a password field.
The underlying database query written by the developer and hidden on the server looks like this. Select from customer where to blues are named and then it drops in whatever the user typed.
Yeah.
And the TVL password, then it drops in the user's password.
So in a normal, benign interaction, the developer expects the user to type a string like Bob and a password like password123.
The database evaluates those two conditions. If both are true, Bob is granted access.
But the attacker doesn't type Bob in the username field. The attacker types exactly this string, or R11 fine.
Let's break down the syntax tree of that payload. Let's look at how the SQL engine parses it. What is the function of the very first character, the single quotation mark?
The single quote is the breakout maneuver. When the attacker types that quote, it acts as a closing delimiter.
The developer's query had an opening quote, ready to accept a name. The attacker's quote prematurely closes that tbluser name data field.
The database parser thinks the username input has finished, and it evaluates the username as just an empty string.
And because the username string is artificially closed, the SQL interpreter assumes that everything following that quote is not data, but executable SQL command logic.
The attacker has escaped the data context and entered the execution context. So what command do they inject next?
The command is OR11.
This is the mathematical skeleton key. In Boolean logic, an OR operator means that if either the condition on the left or the condition on the right is true, the entire statement evaluates as true.
It doesn't matter that the username is blank and doesn't match anything in the database. Because the attacker appended OR11, and the mathematical statement that 1 equals 1 is universally undeniably true, the database evaluates the entire where clause as true.
The engine says, yes, a valid condition has been met for this row.
But the query isn't finished yet. The developer's original code still has that password check, the ADTBL password equals section. If the attacker doesn't know the password, the query should still fail.
That is where the final elegant piece of the payload comes in, the double hyphens.
The text notes that in structured query language, double hyphens are the syntax used to designate a comment.
It acts as a logical lobotomy for the remainder of the query. By placing those hyphens at the end of their injected logic, the attacker instructs the SQL database parser, completely ignore everything else on this line. Treat the rest of the developer's original query as a harmless developer comment.
The password check is literally deleted from the execution logic before it ever runs.
So the final mangled query that the database actually executes reads, select from customer where T-blue surname or 11, the password requirement is gone.
The database pulls the records, evaluates the one as a read as true for the very first record it finds, and happily logs the attacker into the application.
And because the first user created in a database is almost always a system administrator, the attacker immediately gains total control. All because the web application trusted the input and didn't strip out or sanitize that single quotation mark.
It is a profound failure of trust, it is elegant, it is incredibly simple to execute, and it is entirely preventable if developers use parameterized queries or prepared statements that strictly separate the data from the executable code.
The text advises security testers to systematically walk through every single input field on a web app, every search bar, login box, and contact form, enter a single quote followed by SQL keywords, and watch the application's response to see if a database error is triggered.
But what if the application is vulnerable, but it suppresses the errors? The text introduces a highly complex variant called blind SQL injection.
A blind injection is a severe test of an attacker's patience and skill. The web application is vulnerable to the injected logic, but it doesn't return a convenient error message or dump the database contents to the screen.
It just returns a generic page. The attacker is essentially asking the database questions in the dark.
So how do you extract data if you can't see the output?
You use inference. Testers employ complex Boolean-based or time-based attacks.
In a time-based attack, the tester injects a command that says, if the first letter of the administrator's password is A, pause the database for 10 seconds before responding.
If the web page loads instantly, the letter isn't A. If the web page suddenly takes exactly 10 seconds longer to load, the attacker knows without seeing any data on the screen that the first letter is A.
They then move to the second letter. They extract the entire database byte by byte using nothing but the latency of the server's response.
It's a painstaking, brilliant application of the scientific method to a network protocol. Speaking of server responses, the text points out that error handling in general is a massive vulnerability surface.
Developers love rich error messages during the build phase. They enable debugging mode so that when an application crashes, it dumps a massive stack trace to the screen to help them diagnose the issue.
Debugging mode is essential in development, but it is fatal in production.
If a developer pushes the application live and forgets to turn off debugging, they are essentially handing the attacker a highly detailed topographical map of the back-end infrastructure.
If an attacker intentionally submits malformed input to force a crash, that debug output might display the exact names of the database tables, the physical file paths on the server's hard drive, the versions of the libraries being used, or even fragments of the raw source code.
The text establishes a rigid rule. Developers should absolutely minimize the information shared with end users during an error state. A generic and unexpected error occurred message is the maximum allowable detail.
Log the massive stack trace internally for the admins, but never display it to the browser.
We also need to examine the cryptography testing phase. The source makes a fascinating point that cryptographic flaws found during web application testing rarely involve breaking complex mathematical algorithms.
Testers aren't factoring massive prime numbers.
No, they're looking for human implementation errors. They're looking for administrative laziness.
Exactly. They look for the use of weak, predictable random number generators, which allow an attacker to guess the next session token the server will issue.
They look for the use of deprecated encryption ciphers that can be cracked with modern hardware. They look for configuration failures, like an application that supports HTTPS but doesn't strictly enforce it.
Allowing an attacker to force a downgrade attack and capture traffic in unencrypted HTTP.
Or they look for the use of self-signed certificates in production environments instead of certificates purchased from a trusted certificate authority. The math is solid, the implementation is flawed.
And then there is business logic testing, which might be the most challenging aspect of AppSec to automate. This doesn't rely on coding syntax errors or unescaped characters. It relies on exploiting the fundamental flow of the application.
The text defines business logic as the prescribed procedure a user is expected to follow to accomplish a specific goal.
The textbook's example is illustrative, a wire transfer application at a bank. The intended business logic dictates a sequence. First, the user requests a transfer.
Second, the system verifies the user has a sufficient balance in their account. Third, if the balance is sufficient, the system deducts the money from account A and adds it to account B.
Business logic testing involves finding creative, unexpected ways to bypass or subvert that sequential check. It requires human ingenuity.
For instance, what happens if I manipulate the request parameters and attempt to transfer a negative amount of money?
If the developer didn't anticipate that, does the system perform the math, subtract negative $1,000 from my account, effectively adding $1,000 to my balance?
Or what about concurrency issues? What if the attacker utilizes an automated tool to initiate 100 simultaneous transfer requests at the exact same millisecond? Does a race condition occur?
The system might check the balance for all 100 threads simultaneously, see that you have enough for one transfer, approve all 100 threads, and execute the transfers before the database can update the balance,
plunging the account into massive negative territory while creating real funds in the destination account.
That is the true art of the discipline. It requires a human mind to look at the intended happy path flow of the application and ask, how can I sequence these events out of order to break the logic?
And finally, the text brings us back to client-side testing. This circles back to our deep dive on JavaScript. Client-side issues materialize when the application relies too heavily on code executing on the user's machine to enforce security boundaries.
The cardinal rule established here is that client-side controls are fundamentally insufficient on their own. They must be viewed purely as a convenience for the user interface, never as a security boundary.
If a developer uses a client-side JavaScript routine to ensure a user can only select a maximum quantity of 5 items in a promotional shopping cart, an attacker can simply open their browser settings, disable JavaScript entirely, bypass the validation check, and submit an order for 10,000 items.
If the server-side logic doesn't perform a secondary authoritative check, the business logic fails.
The text also instructs testers to deeply examine the local storage of the browser to ensure the app isn't caching sensitive information, like unencrypted API tokens or passwords, on the physical hard drive of the client machine.
Okay, we have comprehensively mapped the architecture, we've explored the dialects of the web, we understand the vulnerability landscape, and we've walked through the testing methodology. Now we need to open the toolbox.
What is the actual arsenal? What are the practical tools of the trade that attackers and security professionals utilize?
The source material makes an incredibly empowering point here for those just starting out. You don't necessarily need a sprawling, expensive suite of specialized hacker software to begin analyzing web applications.
The most fundamental tools are likely already open on your screen right now.
The text explicitly points to everyday standard web browsers like Mozilla Firefox and Google Chrome. If you simply press the F12 key on your keyboard, a vast hidden landscape opens up the built-in developer tools.
For an application security tester, those built-in developer tools are the initial scouting equipment. They grant you the ability to view the raw parameters of every HTTP request leaving your machine.
You can examine the structure of session cookies. You can view the network waterfall to see exactly which third-party scripts are loading.
And crucially, you can tamper with the page locally. You can edit the HTML structure of a live page on your machine, unhide form fields that the developer marked as hidden, change the maximum length values of input boxes, and then submit the altered data back to the server to see how its back-end validation reacts.
It's an incredible amount of power built into a free consumer product. But when an assessment requires heavy lifting, when you need specialized, aggressive capabilities, the text points to the undisputed heavyweight champion of penetration testing platforms, Kali Linux.
Kali Linux is a Debian-derived operating system meticulously curated and packed entirely with free, open-source tools specifically engineered for offensive security, reverse engineering, and penetration testing.
The text notes that the tools required for this specific battlefield are conveniently categorized under the Kali Web Application Analysis application menu.
And the beauty of the Linux architecture is its extensibility. If a specific tool isn't pre-installed, a tester can simply open a terminal, use the command line apt-get install followed by the package name, and instantly pull a new weapon into their arsenal from the repositories.
And among the hundreds of tools within that ecosystem, the text highlights one in particular as an absolute, non-negotiable necessity for web app testing.
Burp Suite. Burp Suite, specifically its proxy functionality, fundamentally changes how a tester interacts with the web.
In a normal browsing session, your browser creates a request and fires it directly down the wire to the web server. It's a direct, instantaneous line of communication.
Burp Suite intercepts that line. It configures itself as a man-in-the-middle proxy sitting locally on your machine, directly between your browser and the external web server.
The text provides a visual figure of Burp Suite in action, and it's illuminating. It shows the proxy intercepting a standard G-key request destined for a target website. But the request hasn't left the machine. It's frozen on the screen.
The tester can read every single line of the raw HTTP transaction, the host header, the accepted encoding formats, the user agent string, the referral URLs.
Because the proxy intercepts and holds the traffic, it effectively stops time. The tester has complete control over the data before the server ever sees it.
They can manually click into that text window and manipulate the request. They might change the user agent string from a Windows desktop browser to a mobile iOS device to see if the server routes them to a different, potentially more vulnerable mobile endpoint.
They can inject a malicious SQL payload directly into a section cookie value, an area normal users can't easily reach.
Once the manipulation is complete, they click a button to forward the poison request to the server and observe the response.
And Burp Suite isn't just for manual tampering. It contains powerful automation features, crawling spiders to map the site, automated scanning engines, and brute force intruder capabilities that can take that frozen request and rapidly test thousands of payload variations in minutes.
The text also notes an open source alternative that provides highly similar capabilities, called the Z-Attack Proxy, or ZAP.
And ZAP is actually maintained as an OWASP project, which ties back perfectly to the community-driven defense model we discussed earlier.
Both Burp Suite and ZAP are foundational. If you cannot manipulate the space between the client and the server, you cannot effectively test an application.
Finally, the text introduces a different classification of tool, Wapiti. This is a web application vulnerability scanner, but the text makes a point to note its operational methodology. It uses a black box approach.
Which brings us back to our discussion on DAST dynamic application security testing. Wapiti is a pure DAST tool. It requires zero access to the underlying architecture.
It doesn't inspect the source code. It doesn't look at the server configurations. It treats the target application purely as an unknown black box, and it interacts with it entirely from the outside over the network, exactly like a real attacker would.
If it can't see the code, how does it discover the hidden vulnerabilities? The text explains that Wapiti utilizes an automated technique known as fuzzing.
Fuzzing is basically the application of chaos engineering to a user interface. So how does that differ from a brute force attack? Is fuzzing just like trying a million different passwords in a login box until one finally works?
No, brute forcing or credential stuffing is highly structured. You are trying to guess a specific valid value. Fuzzing is intentionally destructive.
To use a physical analogy, if brute forcing is trying every key on a massive keychain to see which one cleanly turns the lock, fuzzing is taking a handful of random debris pieces of metal, plastic, paper clips, chewing gum, and sand, and violently shoving it into the keyhole just to see what makes the internal tumbler snap, error out, or shatter the mechanism entirely.
So Wapiti systematically crawls the target website, maps out every single input vector, every search box, URL parameter, hidden form field, and cookie, and then bombards those inputs with massive amounts of random, malformed data, excessively long strings, and known attack payloads.
It fires the barrage and watches the smoke. It analyzes the HTTP responses purely to see how the application reacts to the fuzz.
Does the server return a 500 internal server error? Does it spit out a PHP stack trace? Does it inadvertently reflect the injected script back onto the page, indicating an XSS vulnerability? It's an automated method of shaking the application violently to see what loose code falls out.
And when you combine the automated, chaotic discovery power of a fuzzer like Wapiti with the precision, time-stopping manual manipulation of a proxy like Burp Suite, a security tester is equipped with an incredibly potent toolkit for assessing and ultimately securing a web server's public-facing defenses.
This has been a massive, intense exploration. We have covered an incredible expanse of technical territory today, pulling directly from the foundational concepts in the source material.
So let's distill this into the core takeaway for our listeners, particularly the students meticulously tracking with Dr. Schuessler's curriculum. The fundamental realization is that web servers are no longer static digital billboards.
They are highly complex, deeply interactive, dynamic ecosystems.
They are built on an overlapping web of scripting languages like PHP and JavaScript. They rely heavily on the integrity of third-party frameworks, and they are intimately connected to massive back-end database vaults through intricate ODBC, OLEDB, and ADO plumbing.
And because they must remain dynamic, and because they must remain open to the public internet by design, they are inherently perpetually vulnerable. You cannot rely on a network firewall to save you.
Understanding the architecture, understanding precisely how a server receives, parses, and processes untrusted, anonymous user input from a seemingly simple web form is the only way to defend against devastating application layer attacks.
You have to learn to think like the adversary. You have to map the hidden architecture, creatively test the authorization logic, and relentlessly fuzz the inputs before the attacker does.
I highly encourage all of you to explore the description attached to this session for access to additional resources, study guides, and tool links that will help you practically apply these concepts.
Also, take the time to review other deep dives and explorations we offer to continuously learn and level up your career trajectory.
Specifically, you should explore the related sessions we host focusing on digital forensics, as well as our intensive explorations into network and system security. Expanding your operational knowledge across those intersecting domains is crucial for a holistic understanding of modern IT.
The threats do not operate in silos, and neither should your education.
Exactly. And looking ahead to our next session, we will be advancing to Chapter 11, where we leave the wired infrastructure behind entirely and venture into the invisible, omnipresent world of hacking wireless networks. You absolutely won't want to miss that transition.
Before we conclude this session, I want to leave you with a final provocative thought to ponder, a question that builds on the technological trajectory we've discussed today.
We analyze the emergence of IaaS interactive application security testing, where highly advanced automated agents sit directly inside the runtime environment, monitoring data flow and memory allocation in real time.
As these automated AI-driven security tools become increasingly sophisticated at autonomously catching syntax errors and technical flaws like SQL injection, will the manual human art of finding creative business logic flaws become obsolete?
Or will human attackers, driven by economic incentive, simply evolve their methodologies to map and exploit the blind spots of the automated AI agents themselves? It is the eternal, high-stakes game of cat and mouse that defines this industry. Master the attack, fortify the defense. Until next time, keep your hands on the keys and your network secure.